In this final presentation on light, we will look at some examples of using the thin lens formula. So in our first example, we have a converging lens that has a focal length of 32 centimeters. And the question is, what is the location of an image, Q, that is formed and the magnification when the object is located at a distance of 72 centimeters from the lens? So it's far away from the lens. The focal length is 32 centimeters, so I'm putting the object so that it's more than 2 focal lengths away from the lens. And then I want to repeat that for when the object is located only 20 centimeters from the lens, so that when it's between the focal point and the lens. So we're going to focus on the first one. For each of these cases, we're going to describe whether the image is real or inverted, real or virtual, upright or inverted, or larger or smaller. So let's go back and read the question again and write down what we know. So we have a converging lens that has a focal length of 42 centimeters, so we know the focal length. We want to determine the location of the image Q that's formed when the object is located at 72 centimeters. So our object location is 72, and we're trying to determine our image location. We know that according to the thin lens formula, 1 over the object distance plus 1 over the image distance is 1 over the focal length. We're trying to determine the image distance, so we can rewrite this expression by subtracting 1 over the object distance from both sides. And I find that 1 over the image distance is 1 over the focal length minus 1 over the object distance. So we can use that expression. 1 over the image distance is 1 over the focal length, which is 32, minus 1 over the object distance, which is 72. I can put in my calculator 1 over 32 and 1 over 72, divide those. If I put in 1 over 32, I get 0.03125, and then the units are 1 over centimeters. If I put in 1 over 72, I get 0.01389. It's really important when you're using the thin lens formula to keep a lot of digits in your answer. So I kept, I have that first 0 in there, but then I kept an additional 4 digits in my answer. If you round too much when you're using the thin lens formula, you will get an incorrect answer in the end. So I found that 1 over the image distance is the difference between these two numbers. If I take 0.03125 and I subtract 0.01389, I get that 1 over the image distance is 0.017361. This is not my answer for the image distance. This is 1 over the image distance. If I want to solve for the image distance, I have to cross multiply and figure out I have to get this image distance so that it's in the numerator. So if I cross multiply, I can bring the number down on the bottom, and I can bring that distance that I'm interested in, that image distance, up on the top. And I get that the image distance is 1 over 0.017361. If I divide 1 by that number in my calculator, I get that the image is located a distance of 57.6 centimeters from the lens. So I have determined what the image distance is. I also want to determine whether the image is real or virtual, upright or inverted, larger or smaller, and basically find the magnification. So I know that the magnification is just minus the image distance over the object distance. I found my image distance to be 57.6. My object distance is 72. There's an overall minus sign in front of this. If I divide 57.6 by 72, I get 0.8 with a negative sign out front from that minus that was in the formula. The negative sign out front here for my answer tells me the magnification is negative. When the magnification is negative, that means that the image is inverted and real. The number itself, without the plus or the minus sign, that number is less than 1, and that fact that it's less than 1 tells me that the image is smaller than the object. So I can repeat the same question, except for the case when my object is located at 20 centimeters instead of being located far away. So it's basically located close to the lens. So my focal length of my lens is still 32 centimeters. My object is now located at 20 centimeters, and I want to determine where is the image located. So as before, I know that 1 over the image distance is 1 over the focal length minus 1 over the object distance. I can plug those values in. 1 over the focal length is 1 over 32 minus 1 over the object distance, which is 1 over 20. 1 over 32 is 0.03125. 1 over 20 is 0.05. So I would take this number and I would subtract the 0.05, and I have that 1 over the image distance is a negative value now because the 0.05 is actually a larger number than the 0.03125. So 1 over the image distance is a negative value of 0.01875. This is 1 over the answer. To find the actual image distance, I have to cross multiply. So the minus sign comes over to the other side, and I would divide 1 by 0.01875, and I get that my image distance is now a negative 53.3. The fact that the image distance is negative is going to tell me that it's actually a virtual image, and the image is located on the same side of the lens as the object. But we can see that also more clearly as we look at the magnification. So we can determine the magnification for this case, and that will also help us understand if it's a real or virtual image, upright or inverted, larger or smaller. So we know the magnification is just minus the image distance over the object distance, and our image distance is negative in this case. So our image distance is negative 53.3. Our object distance is 20 centimeters. This negative sign and that negative sign multiplied together give us a positive value for our magnification, and then 53.3 over 20 is 2.67. So the fact that our magnification is a positive number tells us that the image is upright and also virtual. So anytime we have a positive magnification, it's always going to be a virtual image, and that magnification ends up being positive because our image distance was negative. The number itself, in terms of the magnitude of the magnification, is greater than 1, which means that our image would be larger than the object. And that's something that we saw when we looked at the geometric optics and we saw how images were formed by converging lenses. Another example that we have is just slightly different. So an object is located 20 centimeters in front of a lens, and it forms an image on a screen 5 centimeters behind the lens. We want to determine what is the focal length of the lens, what is the magnification of the image, and we want to know if the image is real or virtual, upright or inverted, larger or smaller. So the fact that I know where the object is placed and I know where the image is located, I should be able to calculate what the focal length is. So our object is located 20 centimeters from the lens. An image is formed on the screen 5 centimeters from the lens, and we want to determine what is the focal length of the lens. So we know, and we also want to know what the magnification is. So we know that 1 over the object distance plus 1 over the image distance is 1 over the focal length. So 1 over our object distance of 20 plus 1 over our image distance of 5 has to equal 1 over the focal length. So I can put 1 over 20 in my calculator and I get 0.05, and I can put 1 over 5 in my calculator and I get 0.2. I can add those two quantities together and I get 0.25. That does not tell me the focal length, that tells me 1 over the focal length. So 1 over my focal length is 0.25. I have to cross multiply in order to figure out what the focal length is. So my focal length is 1 divided by 0.25, and it's 1 over centimeters. 1 over 0.25 is 4, so my focal length for this particular lens must be 4 centimeters. I also want to determine what the magnification is, and I know the magnification is just negative the image distance over the object distance. So if I plug in my image distance is 5 and my object distance is 20, there's an overall minus sign in front, and I end up getting my magnification is negative 0.25. The fact that I got 0.25 here and 0.25 in the last case was just kind of a fluke of the numbers that I used. The fact that my magnification is negative tells me that the image is inverted and real. All inverted images are real. And the number that's the magnification, the magnitude of the magnification, that number is less than 1, which tells us that the image is smaller than the object. So we can either solve for the image distance, which we looked at in the first two examples, or if the object distance and the image distance are given to us, we can solve for what the focal length of that particular lens must be. So there's a couple of questions that we can now go back and think about in terms of the human eye, and this is just sort of a follow-up to some things we talked about earlier. Is the lens in the human eye a converging or a diverging lens? And the answer to that is that it's a converging lens. It has to be a converging lens because we have to form a real image on the back of the eye. And so diverging lenses always form virtual images. You have to look through the lens to see the image. So the eye is here. There would be an object located out here. We've got the lens that the light from the object passes through the lens of the eye and forms an image on the back of the eye. Does the lens have a fixed focal length or does it vary? This is kind of a weird question, but the idea behind this question is that lens is flexible. It's made of a flexible material, and so the focal length of that lens can vary as the shape of the lens is changed. And the ciliary muscles actually allow that change in the shape of the lens that changes the focal length. The image that's formed on the retina is inverted because all real images formed by lenses are inverted, so it is inverted, and our brain just interprets that and switches it around. The other thing that I mentioned just a second ago is the ciliary muscles, and what function do they serve? Well, they hold the lens in place, but they also serve to adjust the shape of the lens, and by changing that shape, you change what the focal length of the lens is and allows you to focus on things that are farther away and also things that are a little bit closer. As we talk about the human eye, I wanted to point out that there is the optical nerve, which is located right here in our picture. And where the optical nerve is located, there are no detectors for the eye. There are no rods and cones. And so essentially, at that particular location, there's what we would call like a blind spot. There's a place that as the image is formed on the eye, the back of the eye, there's no detector there to see the image. So we have a blind spot, and I love to do this in class because it's pretty cool. I think you probably could do this if you have this on your full screen, but if you want to see your blind spot, you can point your nose between the cross and the circle, and if you cover your left eye and stare at the cross with your right eye, you can move towards the computer screen while staring at the cross with your right eye, and at some point that black circle will actually disappear. And I just tried it on my screen and I was able to see it disappear. So it's kind of a neat little thing that you can try to do, and you can see your blind spot. And essentially that's the place where that optical nerve is not being able to detect any image. Now, the reason that you don't have a blind spot with both of your eyes is because the other eye compensates when looking at the image. So you can only see your blind spot when you cover up one eye. And you have a blind spot in both eyes. It's just when you're using both eyes, you know that blind spot is not visible. The other thing I just wanted to mention quickly is this idea of polarization, because we use sunglasses that are polarized. And what polarizers do is they basically take light. So here's a flashlight right here. And the light is oscillating and traveling in all possible directions. And what we can do is we can say that we can sort of resolve all of those into directions which are horizontal and directions that are vertical. And if we have light that's not polarized pass through a polarizer, what it does is it takes away all of the light that's vibrating. Let's say if I have a horizontal or a vertical polarizer, it takes all the horizontal polarized light and it takes it away so that only the vertical light can pass through. So if you have two polarizers which are vertical, then the light will be able to pass through. But if you took and you had a vertical polarizer and then you put it next to a polarizer which was a horizontal polarizer, and you put them next to one another, then you get a situation where no light is actually going to pass through that filter. So, and of course, you can have some situations where you have things in between this, where you rotate it and you can see it. This is similar to a wave on a string that's passing through a fence. If you put it through the slots on a vertical fence and then another vertical fence, you can certainly still create these waves. But if you pass it through a vertical fence and then try to do the same thing where the vibrations are now just vertical, and you try to make it horizontal, you can't get the wave to pass through. So polarization is used frequently in a lot of different things, and there's some demonstrations that you can see for that. Certainly sunglasses, a lot of sunglasses are polarized, camera lenses can be polarized, and there's a nice YouTube video that shows some examples of polarization.